Now, for those who have done fluid mechanics or even thermodynamics in the 40 days, you have come across this expression here. You have come across this expression. Okay? This is a very basic, fundamental expression, and it's called, it makes use of continuity. Okay? And Bernoulli uses principles of continuity and conservation of mass, energy, continuity to derive this expression here, this relation here. Okay? It states that the pressure, very important for a steady, it is for a steady, for a steady, so the flow is steady, right, very important. Implicit, what's the meaning of implicit? Anybody what's the meaning of implicit? Implicit, call some names. Atomic sheet, where's the atomic sheet? Throw away all zero, zero. Atomic sheet, what atomic sheet? There's I'll put something there, but okay. Maybe Ahmad, where are you, Muhammad? Ahmad, where are you? Ahmad, absent, where are you? Don't laugh, I don't want. That is not Muhammad, laughing, What's your name? Muhammad? Are you Muhammad? No lah, don't laugh, Muhammad absent, so make sure nobody sign for him today, Laugh, laughing. Okay, next guy. Hakim, where are you? Hakim also absent, Okay. Hakim, sure. Hakim, okay. Must check your photograph on the. Okay, my question, please. Answer my question. My question is, what is my question? Do not pay attention, is it? Very important, pay attention. What was the question? What is implicit flow? What is implicit? Yes. What's the meaning of implicit? Means what? Non-viscous. Viscous and versus implicit. Okay? In a non-viscous regime, it's non-viscous. So steady, implicit, and incompressible fluid. So means what? Density is constant, incompressible. Alright? The Bernoulli principle takes the form of P. What's P? It's a pressure. Okay? Pressure. Plus half rho V squared. What rho is density. Okay? V is the velocity of the flow. What is gamma? We have used this symbol before. Gamma is what? What's gamma? What's the name for gamma? What do you call it? What's the technical name for gamma? No, not symbol, not a Greek symbol name. What does it mean? Gamma? Specific weight. Specific weight is equal to specific is equal to density times G. Density times G. Okay? And Z is of course the height above a data. The height above a data. A reference point. In other words. Okay. So because continuity and conservation energy conservation mass. So this, whatever here is P1 plus half rho P1 square plus gamma Z1 will be equal to the same term on the right hand side, except the subscript will be 2. Okay? So we have P1 here, we have P2 here. We have rho, and because rho is constant, so rho and rho will be same. P1 here, we have P2 there. Z1 here, we have Z2 over there. Okay? Right? Now, so bear in mind, these are the conditions where this Bernoulli equation will apply. Okay? Steady flow, incompressible flow, frictionless, inviscid, non-viscous. Okay, non-viscous, frictionless, non-viscous, and a flow along the streamline. This is the condition. Okay, so P, to be specific, is the static pressure. Static pressure. Okay, static pressure of the flow. So static pressure doesn't mean the flow, there's no flow. Doesn't mean there's no flow. It's a flow. Okay? And the term static pressure is used when you want to open up a hole somewhere along the pipe and you tap the pressure. The pressure reading is the static pressure reading of the flow. Okay? Static pressure reading. As opposed, as you learn later, opposed to stagnation pressure. Static pressure and stagnation pressure are different. Okay? Again, the static doesn't, the flow is static, there's no flow, no. Still flowing. You open the hole and connect to a YouTube manometer. The flowing fluid will give you a pressure reading, and that is a static pressure reading. Right? Okay, and okay, I mean this is a thermodynamic ideal gas equation. I hope you know. PV is equal to MRT. Okay, mass. This is a gas constant. This temperature must be Kelvin. Pressure times volume. Okay, just to refresh your memory. Right. So remember, static pressure is different from stagnation pressure. Okay. So the static pressure. The next term actually is, if you like to put it that way, is actually is dynamic pressure. Dynamic in the sense that it's linked to kinetic energy. It is linked to in a half rho V square. It's linked to kinetic. You see the D here, this is moving. It's moving. So a fluid of elemental volume is moving. It has what? Kinetic energy. Then we have gamma Z. Okay, the last term is hydrostatic pressure. By virtue of the point of reference inside the flowing fluid, okay, it has got a certain pressure called the hydrostatic pressure, or sometimes it's called related to potential energy term. Due to the height, any energy due to the height is potential energy. Any energy due to flowing, any moving is kinetic energy. Okay? So these three terms here represent the total pressure of a flowing fluid element. Total pressure. Okay? Right, so as I said earlier, okay, this relation, whatever subscript on the right is 1, whatever subscript on the left will be 2. Okay, and this is always the case for a free flowing fluid, a free one, no obstruction, just free flowing. Okay, later on you see what happens if you have a turbine below. And turbine is a very practical thing because it's a dam. In a dam, you know, you build a dam and the water levels up there, and when the dam gates are open, it allows water to flow, like waterfall. In the process, you can have a turbine to generate electricity. Okay? And sometimes this turbine is inside the conduit. It's not open exposed, it's inside the conduit. It flows through, in order to capture the maximum energy. The turbine is placed usually as part of the flow conduit in the big pipe. So as the flow goes through, the turbine rotates, and because there's rotation, there's kinetic energy, and this is used, this is converted to electrical energy. Alright? So if a turbine, then these terms have been modified already. Have been modified. Okay? Now, so turbine is usually downstream of the pipe. Okay, let's say you put away the turbine. What you have a pump instead in the building and you pump. You pump, for example, in your flat, in your apartment, you draw the water, you have a water, you draw the tap, the water comes through. And usually the water is pumped through a header tank. Let's say you don't have a header tank, for example, in a different case, already from a pump to your tap. Okay? So you see the pump is the front over, it provides the pressure, it pumps the water to your tap to open up. So in this case, this expression up there will be modified again. Okay? But of course, in practice, in this you have a header tank, it's pumped your header tank, then it leads to all the households. But there are situations whereby it's pumped straight to your piping, to your tap. So again, in that case, then this will be modified to take into account the pump, or take into account the turbine. Okay? So this is the fundamental basic expression. Free flow. No prime mover, no pump, no turbine yet. Okay. So now, Bernoulli principle. So you have a flow like this. Okay? And if your point 1, let's say, is there, point 1 is there, and point 2 is there. Okay? So the flow goes through. Now, when here you push this fluid all the way up to a certain level, then we balance out the force down, the force upward and the force downward to equalize. Okay? Now, so at this point here, what happens to the velocity at point 2? The velocity of the flow is 0. So V2 is 0. It's called a stagnation point. In stagnation point. Right? And of course here, Z1, what is Z1? In this case, we take a convenient reference. And the convenient reference datum is this line here, the bottom of the pipe, so to speak. So Z is measured from the bottom line, bottom wall of the pipe to this point here, 1. Z1. So Z1 equal to Z2. Okay, Z2 is here, up to this point here. Z2 is distant all the way up to point 2. So Z1 equal to Z2. So you must know what the datum is. Datum, we take data from a convenient common level, common ground. That's what we mean by datum. Okay? So therefore, the stagnation pressure is P2. Okay? P2. And P2 becomes this. Right? P2 becomes this. If you want to put what I just said into this expression here. Okay, P2 is 0, and Z2 will cancel out with Z1. Okay? And because it's all water, so the rho, the gamma, and the gamma is the same. So this one will cancel out this one, and this will be 0. Okay? And even you will have, therefore, the stagnation pressure P2 is simply P1 plus half rho P1 squared. Right? So remember, static pressure and stagnation pressure, the terms are different. Remember the terms. So static pressure and stagnation pressure. Now, next I want to introduce the terminology of head. In pipe flow, usually they refer to head. So what is head? Somebody call it pressure head. So what is head? Head. And what is the unit for head? The unit for head is actually a distance, it's a height. So it's meter, meter. Basically, something is called a pressure head. So it doesn't mean it's pressure per unit meter. Be very careful. Okay? It's head. So therefore, we can actually use the word H to represent these three terms in this expression. Okay, divide by gamma. So every term in the Bernoulli's equation, divide by gamma, will give you the head. Okay, divide by gamma will give you the head. Alright? So the P over gamma is the pressure head, and is d squared over 2g is velocity head, and z is simply the elevation head. Okay, units are all in meters, all in meters. Okay, all this you all know, I will not go through it. What thing on this first expression for power, power. So if the head is so much, okay, and the flow rate in the pipe is so much, expressed by Q and the given gamma. Okay, then the power that the fluid has, the fluid has is given by this expression. Q times gamma times head. Flow rate times specific gravity times the head. Alright? So remember, power, okay, is flow rate times gamma times head. Whatever head that is. Yeah? So this is so what you have, you have a pipe that's slanted. Where's your Z? Where's your Z? Where's your Z? So your Z will have to be from a common point again. Okay? Usually Z can be from a common datum. Okay? From common datum. This is a common datum. So from there to there you have Z1, from there to there you have Z2. Okay? It's not from here to there and there to there. In this case Z1 equals Z2. No, huh? You have normally you have a common, given to you a common datum, and that is your Z1, and that is your Z2. So Z1 and Z2, Z1 minus Z2 is not equal to 0. Huh? Be careful with that. Okay, so this is for, remember the assumption says inviscid flow. It is no friction. I see through in life now. In theory, get no friction, ideal case, but in practice there is friction. There's viscous. This friction is not between solid surface, between fluid and a solid surface, right? So that is called viscous friction. Viscous. So in true life, of course, there is friction. So there's the presence of course, viscosity. Presence of viscosity. So what does friction do to energy in the fluid? The fluid that's flowing. There's energy due to the pressure term, okay? The pressure head, dynamic head, or the velocity head, and then Z. It's slanted. So that's the total energy available. But when the flow goes from point 1 to point 2, and has got to, and there's friction. Now we take consideration friction, viscous force. So what happened to the energy? What happened to this total energy when it reaches point 1? From point 1 it reaches point 2. What happened to the energy? Is the energy the same at point 2? Well, all the subscript on the left hand side, 1 equal to all the three terms. Subscript 2, 2, 2. Is it the same? Bernoulli equation remain the same? 3 terms on the left, 3 terms on the right? It won't be. Because you have so much energy at the bottom of the hill, at the bottom of the hill, very national surveys, you point your backpack against the rifle, and you climb the slope, go to the hilltop, Pencang Hill, or Sapi or whatever, Pencang Hill, your energy is the same, same energy, you reach the hilltop, you see the same energy. You're backing away, you're less, you're hungry already. A lot of energy used to climb, plus your friction, also the slope friction, overcome friction. So, point 1 and point 2, energy level is different. So then you must add another term into the expression. Okay? And that expression is your HL. Head loss. You lost your head already, Head loss. This is because energy is taken away from the fluid and it's converted to some other thing. The energy now be destroyed, like it's converted. Okay? Converted to heat or whatever. Right? So you must consider on the right hand side there's the head loss term. Okay? So in other words, the first 3 terms here is greater than the first 3 terms here already. And it's balanced if you have plus the head loss. Because it overcome the viscous damage, the friction. So head loss is positive, always greater than equal to 0. Okay? See? Of course, if no friction, we go back to the first principle. The expression we got from Bernoulli. But in this case, there is friction. So don't forget your head loss, head L. Okay? So now, as I mentioned earlier, what happens if you have here, if it goes from 1, which is point, position 1, position 2, and this is a piping, and you put a turbine there. So just now for 3, 4, you still have head loss. Okay? Head loss is still there. So actual application from this reservoir to this reservoir, you still have the head loss, it's still there. The head loss there. But on top of that, the turbine, what happens to the turbine? It will take the energy from the flowing fluid, the flow fluid, it takes energy from flowing fluid and convert it to what? To electrical energy. So part of the energy in the flowing fluid is converted to electrical energy. So there's loss of some more head, loss of some more head. So loss of head due to the turbine. Must put that term there. Okay? Alright. So then, so what's turbine power in this case? The turbine rotates, it gets power from the flowing fluid. So from the term power that we got earlier, turbine power is Q gamma times head. Okay? Turbine head, let's call it turbine head. Okay? So power is always flow rate times gamma times whatever head you have. Okay? Now, instead of a turbine, if you move with the turbine, let's say, as I mentioned earlier, in the tap, you have a pump that pumps the water all the way to your tap. Okay? So, this pump actually so-called add energy. That's it, not correct for engine to say add energy. You cannot really create, when we say add energy, this energy is created somewhere. It converts energy from the pump, rotation of the pump, the kinetic to the pump, into the flow. So energy is added or converted from the rotation of the pump to your fluid. So in this case here, you on the left hand side, you will therefore put a glass head of the pump. Glass head of the pump. Okay? Glass. But because usually we like to put all the heads together on the right hand side, so you move the head of the pump, which is positive, to the right hand side becomes negative, minus the head of the pump. Okay? So you put all the heads together. And don't forget there's still head loss because of viscous friction. Head loss is there. Turbine not there. In the domestic piping, turbine not there. So the pump and the loss, the head loss. Alright? Now, so in the case you have a complex situation, you have a pump, you have a flow, then you have a turbine, then of course all the heads must be there. That's the case. But bear in mind the sign. Okay? Head loss on the right hand side is positive, and the turbine head is positive, but the pump head is negative. Because right, the pump head should be on this side. Right? I'm going to put all the heads together, so we put the right side. So you have heads of water flowing through a turbine to generate power, producing electrical energy. Now, so of course, so this is a very simple exercise. Let's look through it. Go through it. You have water flows from a lake to the turbine. That's a turbine. Okay, as shown in the figure below. Consider the flow is steady and incompressible. Okay, steady and incompressible. You cannot say illicit. So you must consider the viscous friction. Okay. It's incompressible, rho is constant. Calculate the maximum power that a turbine can extract from the water, and given the specific weight of water. Okay? Given the specific weight of water. So in this case here, where do we start? How do we start? You want to get the maximum power that the turbine can extract from the water. Okay, what's the turbine power? S power, huh? Not super power, but power. You're like superhero, right? Okay, S, huh? Power, turbine, T, turbine. And just to refresh our mind on the so-called formula, you like formula, is flow rate times the static weight times the turbine head. Okay? Turbine head. You can call it equation 1 if you like. So what's the flow rate? Q. What's the flow rate? Q? In this example here, Q we know is area times the velocity. Area times velocity. So is A times the velocity, and A is about area at 0.2 times the velocity at 0.2. So what's the area? We are given what's the cross-sectional area? Circular, a kite circular. So it's pi r squared. On the diagram, we are given the diameter is 1 meter. So yes, pi radius is 0.5 meters and r squared, and velocity is 8 meters times 8. So we get a Q for 6.28 meter cube per second. Okay. So next, what do we do now? We have to calculate the turbine power. So you have a Q, but you know your HD or not? So must find your HD, turbine head. Okay, the turbine head. So we use the Bernoulli's principle for the expression where at point 1, the top free surface of the leg, free surface, E1 over gamma plus D1 squared over 2G, okay, plus Z1, okay, is equals to D2 over gamma plus D2 squared over 2G plus Z2 and plus what? HD, HD. Is that correct? Anything missing from there? What about HL? What about HL? Don't forget, it never mentioned implicit. The question never mentioned implicit. So you cannot assume frictionless flow. Okay? You assume frictionless flow. In this case, L equal to 0, I saw wrong already. Okay? So can I assume that H L is 0? I told you already. This is the real situation. In practice, water flowing, in the dam, and water flowing through a turbine generating electrical power. It's a real situation. How can you assume frictionless flow? In practice. So HL is there. HL is there. Don't forget. Very important. Now, here we call it 2. So what can we say in this equation 2 or expression 2? What can we say? Can we start to cancel some terms? Can we start to cancel some terms? Okay, what is V1? What is V1? V1, okay, no, V1. V1 is the water level at the surface of the lake. You think to generate turbine power, the lake level of the lake will go down, look like that? It won't, it still stay there, right? You see, in generating power, the lake still same height, the water level is same height. So V1 approximately equal to 0. Okay? So now we can say that V1 equal to 0. The level of the lake don't go down like that. It just stays the same because it's a very big lake. Okay? Okay, what's P1? What about P1? P1. P1, what is P1? Anybody? Equal to 0 because we're actually talking about gauge pressure. So P1, 0, and what else? What about Z1? Also 0. What is Z1? 0.1. Where is its height from? What is the best datum here? Datum has been placed in underlying form for you already. That's the datum. So Z1 is not 0. Z1 is close to 150 meters. Okay? On the right side, P2 equal to gauge pressure 0. Okay? What else? Z2. Where is Z2? Distance of point 2 from that reference open line is 0. So we simplify equation 2 already. So equation 2 now becomes 150. This is your Z1 is equals to D squared. D squared is 8 squared over 2G. G is 9.81. Okay. Plus HL plus HT. Oh, HL plus HT, So we still got, we cannot find HT. What's HL then? What is the head loss due to viscous friction? Anybody? Lim Yan Chun, are you here? They so no 100% attendance. Everybody sign for 100% attendance. Don't play for your friends. I know Mama is absent. Lim Yan Chun absent, Lim Yan Chun also absent. Are you sure Lim Yan Chun? Yeah. Okay. Lim Yan Chun, yes? What again? What's HL? Anybody can help Yan Chun? Anybody can help me? Anybody? Muhammad Hafiz. Where are you? Oh, who's Hafiz? Muhammad Hafiz bin Anwar. Where are you? In Anwar? Okay, in Anwar, yes. Okay, come Hafiz. Let's get some class participation. I hope everybody fall asleep. Time really. Okay. Alright. For the other Hafiz, what's the other Hafiz? In Manchno. Huh? No answer. What's HL? What's the value of HL? Anybody can help your friends? Anybody? The ladies, very quiet, the ladies. Smiling. But no answer. Ladies, give your time. Remember this one, right? In the exam, we must study the question. What did the question say? What did the question say? What did the question say? Maximum, right? It's a magic word, maximum. You miss it only, that's it. Already. Maximum. So what is the maximum power that the turbine can extract from the flowing fluid? Maximum will be, that means if there is no friction. Maximum is if there is no friction, the maximum power will be so much. So it means L equal to 0. Okay. equals 0 for maximum turbine power. Turbine TUR, the turbine head, turbine power. Okay, so 0. So therefore, HT is equals to 146.7 meter. So therefore, putting it into equation 1, you give turbine power, just substitute, will be 9 times 10 to the power of 3 kilowatt. Answer. Okay? Right. Okay, I know. I'm also thirsty and hungry also. Okay, so today we covered many work examples.